Hi everyone, I'm Professor McBain and welcome back to Chem 100 and welcome back to our lecture series on what is science. This second video in the series is going to be taking a deeper look into what makes claims scientific and how we can build up claims so that they can be more trustworthy, more backed by science, and so on. Welcome to part B of our lecture. For lecture 7, what is science? As some of you may know, I share an office with 5 other people, so please forgive any sounds that might sound like someone opening and closing doors as they come in, but we're going to stay as focused as possible. All right, so when I left you, we were here talking about characteristics of a scientific theory, and I got to tell you that one of the most important characteristics of a theory is that it postulates nothing unnecessary. Okay, so what does that mean? Well, it basically follows Occam's razor, which states that the simplest explanation is often the correct one. Okay, but what does that exactly mean? So why don't we page over to this little Word document that I've prepared that will hopefully help guide you in writing your notes. Okay, and as I show you these, you're welcome and encouraged to press pause as often as you need to write down the notes that you need to help this stick in your brains and for you to have as thorough of a textbook as possible. All right, so again, Occam's razor basically states that the simplest explanation is often the correct one. So go ahead and write that down in your notes for this slide. All right, did you do it? All right, let's get back to the slideshow. All right, it also needs to be logically consistent. So next week when we give our unit on baloney is just basically going to be a unit on detecting logical fallacies and avoiding them as we write good, sound arguments to support our claims. Okay, so but for right now, just know that characteristic of a scientific theory is that it needs to be logically consistent. Okay, it needs to make sense, basically. It also needs to be logically and empirically falsifiable. In other words, there must be some cases which could exist in which the theory could be imagined to be invalid. So again, I think it's a little bit difficult for most of us to imagine a world in which apples wouldn't fall, but if you could imagine that apples would suddenly not fall, then maybe that would help you imagine the case in which Newton's gravity laws would be incorrect. Okay? So here's some more notes for you. So again, cases must exist in which the theory could be imagined to be invalid. And so if those cases arise, they refute the hypothesis or they at least prompt us to modify our hypothesis to further describe those cases. So one example is like maybe you could make the claim that all swans on this big wide world are white. But that claim would be refuted as soon as someone observes a black swan. That would tell you, no, not all swans are white because that's a swan. It's just a different color. All right. Here's another claim that we've been encountering lately. So a few weeks ago, we decided that all molecular compounds do not conduct electricity. We said ionic compounds do conduct because when they dissolve in water, they separate into the ions that make them up, which can conduct electricity through a solution. But molecular compounds stick together in the unit, and they don't dissociate into 2 charged species. So that was what we thought. But that claim was falsifiable as soon as we started getting into Chem Activity 6 last week, where we had Dr. Nichols's little diagrams showing that hydrochloric acid actually does light up a conductivity device, okay? But HCl, as you recall, it's made out of entirely non-metallic elements. It's made up of hydrogen and chlorine, and both of those are non-metals, okay? So how can something with all non-metallic elements conduct electricity in a solution? And so that led us to further refine our ideas about molecular compounds. More specifically, we concluded that some molecular compounds are acids, and acids react with water to form ions. And so that's why an acid, such as hydrochloric acid, HCl, can conduct electricity even though it's actually still a molecular compound. Okay, so again, HCl is actually still a molecular compound, but it's an acid that forms ions as soon as it reacts with water. Okay? So, but here's the thing is that if you make a claim that cannot ever be falsified, that claim is not scientific. That's what we call pseudoscience. Okay? If you're making claims that can't ever be disproved, that you couldn't even imagine to be disproved, that's not real science. Okay? So scientific theories are clearly limited by boundary conditions so that it's clear for experimenters whether or not particular observations or data are relevant to either verifying the theory or falsifying the theory. Okay, so there are boundaries about what fits into the data that you're interested in. Okay. The theory also has to be testable, or it has to be able to lead to predictions or retrodictions that are testable. Okay, so I think that most of us are familiar with what a prediction is, but what in the world is a retrodiction? So an example of a prediction would be something that I talked about again today in class, that probably back in the day, a lot of scientists were thinking to themselves, someday when technology is better, we will be able to observe my theory firsthand. So for example, Democritus maybe he imagined in his wildest dreams that someday we would be able to see atoms. And guess what? Now we can. I'll show that to you. Oh, we saw it actually the very first day of class. Yep. So then retrodictions kind of go the opposite way. We take a look back at data that were already gathered years and years ago before the technology had developed us to observe something about that data firsthand, or before a theory had been written up and developed that could explain those data. In other words, we're accounting for data that were gathered in the past which couldn't be explained at the time. Okay, so a lot of immunologists, people who study diseases, do a lot of retrodictions when they take a look at how disease was spread back before there were even concepts of viruses and bacteria. So all of those plagues that came out before the mid 1800s, people tended to attribute them to God punishing people, or sometimes even in the early days of science, they would refer to them as miasma. They would blame it on poor air quality, but often it was something else. And so then with all of the data that people were recording, even though they didn't know how to put it together, now we can often put together certain causes of those disease spreads, those plagues, all right? So in addition to a theory being testable or being able to lead to predictions or retrodictions, sometimes you have to actually make verified predictions and retrodictions with them. It also has to involve reproducible results. So a theory does not support something that can only happen once in a blue moon, well, unless you track a certain number of blue moons, you know what I mean? It has to be reproducible. You have to be able to carry out the same method every time with patience, but also with precision, and be able to get the same results every single time in order for your theory to be proven as sound. Other scientists also need to be able to carry out the exact same experiment that you did and obtain the same exact results that you did. It can't just be something that only you can do. Now, if you've obtained a patent on a certain method or device or something like that, okay, maybe you're not really willing to share that, but let's say that you hired an employee to continue carrying out whatever results you're trying to make money off of. Your employees also need to be able to reproduce those results. Again, it can't be something that only you can do, right? You also need to provide criteria for the interpretation of data as either factual, so it's a fact, you observed it, it's a fact, or artifactual, anomalous, what, or irrelevant. Okay, so let's take one more look at those notes that I've prepared for you. So we tend to have a good handle on what is factual data, so let's take a look at these notes here. All right. So an artifactual observation is something that would not support the claim, support the theory. But it's artifactual because it was some sort of mistake and it was caused by a technological difficulty or some other sort of experimental error. Okay, so if we return to the example about apples falling, okay, so you could imagine that if you're conducting a bunch of experiments about gravity, if one of your scientists, instead of just dropping an apple, decides to throw it up at first before it comes back down, that would be an artifactual piece of data because the experimenter did not abide by the proper method of conducting those gravity experiments. An anomalous piece of data would be a sort of like one-off occurrence that does not fit into the typical pattern. Sometimes they're one-off due to mistakes, sometimes they're one-off due to actually not falling within the bounds of the data set that you're interested in. Okay, so one example, we have not covered this in class, so don't worry about it, but ammonium chloride, which is NH4Cl, is also an ionic compound. Bet you didn't know that. You didn't have to know that just yet, so don't worry. But I'm letting you know that this compound, composed of entirely non-metallic elements, is also ionic. It's weird. So the positively charged portion is the NH4, and the negatively charged portion is the Cl, as we saw last week. Cl tends to take on that singly negative charge, okay? And then we also have some irrelevant data, which you've probably heard of the term irrelevant before, but in the case of science, it's some sort of observation that does not pertain to the hypothesis or theory of interest, even if it is like interesting to the scientist. So, for example, if we return to our studies on ionic compounds and molecular compounds and their conductivity in solutions, we could study the rate at which sodium chloride dissolves, and that may be interesting, but it's not relevant to our goal of classifying the compound NaCl as ionic or molecular. So it would be interesting to look at, but it's not relevant to the study at hand. So moving on, how to tell if a claim is scientific? Well, one of the most important things to keep in mind is whether or not that claim is actually reproducible, okay? And as we said earlier, you have to be able to make predictions or retrodictions about it, okay? So I have here a hyperlink about gallium and germanium, and I will post that, but here it is, okay? So Mendeleev first started writing up the periodic table in March of 1869. So we actually only had zinc with a mass of 65.2 and then arsenic with a mass of 75. But Mendeleev predicted that there would be two more elements right here with masses of 68 and 70, like so, because those were that was the pattern in the atomic masses that that everybody had discovered up until that point. He didn't know it, but that's what they were. And so then years later, we discovered gallium and germanium. And so Mendeleev was able to make the prediction of those two elements being discovered long before they had been discovered, simply because he was writing up his hypotheses in a very, very careful way. Okay. Similarly, some other predictions that often happen are eclipses. So we can predict eclipses that are going to happen now that we know how often they tend to come, and we know the rates at which the moon rotates around the Earth and how that interferes with how we are exposed to the sun at different phases and all of that. But we can also make retrodictions and predict, backwards predict eclipses that happened in the past, and then oftentimes that will sync up with any written history from civilizations that had written history at that point in time. So they have to be testable and they have to be falsifiable, okay? We also have to have adequate supporting evidence about that, okay? So that sort of supporting evidence needs to be collected in an objective manner. It can't be too subjective. But you can't just have anecdotal evidence. That's where we have like, oh, I know a guy who did this. Or you can't also just have personal experience, like, oh, in my experience, I've seen this happen, okay? So that evidence also needs to be observed and collected by someone who is not invested in either the method or the product being deemed successful. They need to be unbiased and just honestly interested in seeing whether or not it works. And so personal experience or anecdotal evidence from friends is not sufficient. You need to have a much more robust protocol to observing whether or not something works. One example that I have in my life right now, sorry again for all of the parenthood examples, but if you've ever heard of the amber teething necklaces, a lot of parents swear up and down by their personal experience and their friends' experience, the anecdotal accounts that they've gathered from their friends. But unfortunately, there are no studies, scientific studies, that can confirm that amber teething necklaces actually reduce the amount of pain that a child experiences due to their teething. And in fact, if you try to establish a mechanism on how it would work in the first place, it doesn't hold up. Also, scientific claims could include or suggest mechanisms. Okay. So we've talked a lot about what science can do. We've talked a lot about the criteria needed for things to be truly scientific and not pseudoscientific. But let's talk about what science cannot do. It cannot make moral judgment. That's not the job of scientists. Maybe scientists can do so on our social media platforms, but ultimately in our work, our job would be something more like presenting data that show how to conduct human embryonic stem cell research, but it's not our job to say whether or not it ought to be done. Science can also not make aesthetic judgments, such as whether music by Beethoven is better than music by Mozart. However, scientists can make correlations between certain aspects that Beethoven's compositions have versus those involved in Mozart's compositions, and correlations between whether those tend to lead to people enjoying those compositions or not, right? So we can do studies on why people might like these things, but ultimately scientists can't be the one to say whether Beethoven is better than Mozart. We also can't answer questions about the supernatural, right? Being supernatural, supernatural entities, if they do exist, they tend to have features that are by nature not observable by typical detection methods, right? Supernatural entities also tend to only be observable by certain people, like say clairvoyants or people with ESP and so on. All of these things that it's not reproducible. It doesn't apply to everyone. There's a lot of anecdotal evidence going around about things. So of course, like if something is deemed to be supernatural, like that's where science stops. We also can't prove a negative. So this one is always a little bit funky to describe, but basically what's going on here in Russell's teapot is that someone has suggested that there's a thing that is not observable, and so it's probably there. And so we can't prove or unprove something like that where the conditions are such that it's not observable. Honestly, this relates a whole lot back to the whole supernatural thing. It's just that it's not ghosty or angelic in nature, right? But it is one of these things like, oh, this thing probably exists, even though we have no way of detecting it. No. In a way, it's almost like an appeal to ignorance, which we're going to talk about when we go to our chem activity on baloney and logical fallacies. Anyway, let's move forward. Scientists cannot find the truth. That's something that's up to religious leaders and philosophers and so on. The truth would be kind of more like, what is the point of life? What is the point of such and such? What is an overarching truth that unifies us and so on? That's not the job of scientists. We also cannot deal with issues of human consciousness and feelings. We can study a lot of chemical relationships between certain emotions and what sorts of chemicals are released in our brains. Neuroscientists are also doing a lot of research into what sorts of characteristics have to be present in a brain or in an animal for there to be a certain level of consciousness. So that's why we say we can't deal with these issues for now, but we sure are trying to be scientific, and we're trying to approach these topics, but without overstepping our bounds. Okay, that's it for this topic. Next, we're going to talk about those logical fallacies. So we're just going to be really, really careful about being scientific and also presenting our scientific arguments in a well-supported, well-substantiated manner. Okay, thanks for joining me.